In our first video, we began discussing an inner product for a general vector space. And it's basically the analogous thing that you get for the dot product in Euclidean space. We're trying to take those same ideas, those same properties, and seeing how we can use those in a general vector space to give us ways of measuring length, talking about orthogonality, and distance between vectors, so on and so forth. In this second video, we're going to continue discussing this and see some other things here as well. So our second example, we'd like to show that if U and V make up an orthonormal set in a vector space V, then the norm off of the, I guess this is the induced norm, is always going to sorry, let me say that again. The distance between U and V using the induced norm, the distance is always going to be the square root of 2 between those two vectors. So this is kind of a strange property because this is for a general vector space. And not only that, we don't even say specifically what the inner product is. But it always turns out that the distance between these two vectors under the induced norm is always going to be the square root of 2. All right, let's go ahead and calculate something here. So we're going to calculate, rather than just the distance between U and V, let's go ahead and calculate the distance squared, because that's going to get rid of the square root. So this is the inner product of this vector U minus V with itself. And again, we don't have the square root here because we've squared this to get rid of that, just to make it a little bit easier to work with. Now let's go ahead and distribute this out using some of the properties of the inner product. So this is going to be the same as the inner product of U with itself minus 2 times the inner product of U with V plus the inner product of V with V. Now I just want to mention here briefly, we've actually used two properties in one. When we were distributing things, we had minus the inner product of U with V, and then we also had minus the inner product of V with U. Now these turn out to be the same if you're talking about real vector spaces, where you're dealing with real scalars, and so on and so forth. If you have complex vector spaces, where you could potentially have complex scalars, or your entries involve complex numbers, then when you switch the order of these, you can't just switch the order of these and they're equal. You end up picking up like a complex conjugate if you switch these. So I just wanted to point that out, that we can only do this because we have real vector spaces that we're talking about here. There's a slight difference if you're talking about complex vector spaces if you run into that. But let's just back up here, so we'll get rid of this here. So just using some of the properties of the inner product distribution, and you can swap the order of the inner product and change things. This gives us the following. This gives us the following if I rotate this back. There. All right, so if you take the inner product of U with itself, that ends up giving us the norm of U squared. This is still minus 2. We don't know what this inner product is, so it's just the inner product of U with V times minus 2. This is the inner product of V with itself squared. But this here is length 1. We know that U has length 1 because they are orthonormal. They're normalized where they have length 1. This is also 1, the length. They are orthogonal as well. That's the first half of it. They're ortho or orthogonal. That means their dot product is 0. And so let's see what we get out of this. We end up getting that the length, or the distance between these two squared is 2. So that tells us that the distance between the two vectors then is going to be the square root of 2. And that's it. All right, let me go ahead and talk about a couple very important inequalities. And these are very important if you continue studying mathematics that involves trying to estimate things. Like, for example, if you take we have a class here at Olivet called Real Analysis, and at some other colleges they have a little bit larger math department, they have a complex analysis course and so on. So if you take some of these courses and kind of continue in that direction, these two inequalities, we lean very heavily into those when you're taking real analysis or complex analysis or functional analysis. And there are even applications into engineering of using these things as well. So the first inequality, very important, is called the Cauchy-Boyakovsky-Schwarz inequality. Sometimes it's just called the Cauchy-Schwarz inequality. So here's what it says. So for any two vectors u and v in an inner product space, the inner product of u and v, if you take the absolute value of it, is at most the length of u times the length of v. And then the second very important inequality, you can actually prove this first one just using facts about quadratic functions, which is really kind of cool, or parabolas. But we'll just kind of skip that proof there. The triangle inequality, again, another very important inequality. So it says, what's the largest that the norm of the sum of two vectors would be? Well, it's at most the norm of the one plus the norm of the other. So let's go ahead and work out an application involving one of these two, or both. Well, let's see what we get as we're going through this. These two very important inequalities to show something just kind of interesting here. So we'd like to prove that this inequality here is true. That a plus b over 2 squared is at most a squared plus b squared over 2. So we could actually prove this using the CBS, the Cauchy-Boyakovsky-Schwarz inequality, with u and v as these two particular vectors. So let's write out the CBS inequality. Here's the CBS inequality. It says that the inner product of u with v, if you take the absolute value of it, it is at most the norm of u times the norm of v. Okay, so let's calculate what the inner product of u with v would be on the left. Well, that would give us, if we take that dot product, that would give us a plus b, which is then an absolute value. If we calculate the norm or the length of that particular vector, we would end up getting the following. So we would end up getting a squared plus b squared under a square root. Now with v, it's similar. The length of this vector, that is the square root of 2. Okay, so what does this give us here? So it says that the left is less than or equal to the right. All right, let's go ahead and square both sides. Since this is non-negative and this is non-negative and we have this inequality established, then you can actually square both sides and it's still true. So that gives us the following. So it ends up giving us a plus b squared is less than or equal to 2 times a squared plus b squared. Or let's just rework this a little bit. If you divide by 2, here's what, well, do we want to divide by 2? Let's divide by 4. So if we divide both sides by 4, here's what we get. Over 2. There we go. So then finally, we have what it is that we wanted, because we can write 4 as 2 squared. And then the left side just becomes a plus b over 2 is less than or equal to a squared plus b squared over 2. So why would we care about this being true? So this is true for not only for any real numbers, but if you had a couple functions in here. Suppose that you had a function a and a function b in here and here. This gives us a way of giving us something a little bit easier to work with, but it could potentially be larger. So like for example, if you wanted to integrate a function a plus a function b over 2 squared, very often when students are in Calc 1 and Calc 2, they say, well, let me just distribute the square because it's going to make things easier to work with. They don't want to FOIL it out because it could potentially make things, maybe integrating a times b is difficult. So they don't want to do this. Well, if you're doing things correct, you can say, well, it's not equal, but it's less than or equal to where it's just a squared plus b squared over 2. So this could be potentially easier to integrate, or whatever the application is that you're working on. But so we've shown that this is true. And the last example that I wanted to talk about is how we can come up with an inner product on the set of continuous functions over the interval from a to b. So if you think back to the previous, or I guess the first example that we talked about, here was the inner product that we had. So you would take any real numbers and you fix them, t naught, t1 through tn, on some common interval. And it turns out that this right here is an inner product on the space, the vector space of polynomials of at most degree n. However, if we choose those points, t naught, t1 through tn, so that they're equally spaced, and we let n tend to infinity, so that it kind of fills out, so basically just like in Calc 1 and Calc 2, we're kind of filling out more and more and more and more of these points, or these kind of nodes. Here's what the inner product becomes. The inner product ends up becoming the following, that it's just the integral over that interval from a to b of the two polynomials multiplied together. And I should mention that t naught, for this to work out, t naught has to be a and tn has to be b. Alright, so it can actually be shown that what we've just discussed here turns out to be an inner product on the set of continuous functions over the interval from a to b. And this is a very common way. There's other ways that you can come up with an inner product on the set of continuous functions, but this is a very popular one. This is a very popular choice that's very often that this is the choice for the inner product that you would use. All right, let's go ahead and work this out, see what it looks like. So use the inner product that we just talked about on the previous slide on the set of continuous functions, or I should say the vector space of continuous functions from 0 to 1 to compute the dot product, or the inner product of f with g, if f is this particular continuous function and g is this other continuous function. All right, let's go ahead and calculate this then. So the inner product of f with g is just the integral from 0 to 1 of 5t minus 3 times t cubed minus t squared dt. So if you end up FOILing this out, here's what you end up getting. You end up getting 5t to the 4th minus 8t cubed plus 3t squared dt that you're integrating from 0 to 1. And so if you take these antiderivatives, you end up getting 5t to the 5th minus 2t to the 4th plus t cubed. This is evaluated from 0 to 1. And so if you plug in the limits of integration, what you end up getting is the following. You end up getting 0 out of this. So this tells us that f and g are orthogonal to each other. And I should put arrows over these because these are vectors. in a vector space. This tells us that f and g are orthogonal to each other under this choice of inner product that we have on the vector space. So these polynomials are orthogonal to each other. And so you can do all kinds of things with this in the set of continuous functions. You can then calculate, so we were able to calculate inner products, we were able to show orthogonality, you can calculate lengths, and so on. Distance between vectors. All right, so it looks like we finished up the section. What did we talk about? We defined an inner product space. Here's the 4 properties that we have on an inner product. And if we have those 4 properties with that pairing that we come up with, we call V paired with that pairing an inner product space. This gives us a way of checking orthogonality of vectors. It gives us a way of, and I should say that in our last example, a very popular inner product on the set of continuous functions is what we just talked about in the previous example. So from there, we can talk about all kinds of things. We can talk about the length from that induced norm. We can talk about the length or the induced norm based off of that inner product. We can talk about distance between vectors. We can do estimation using the Cauchy-Schwarz inequality or the triangle inequality. All kinds of interesting things. Okay, so we've officially finished section 6.7. Go ahead and finish up any remaining MyLab homework problems.